So regarding the irrationality of root 2, all right, so theorem 2 down here, we're going to use proof by contradiction. So suppose root 2 is indeed a rational number, which would imply that it may be expressed as the ratio of two integers p and q, as follows. Root 2 is equal to p over q. Step number 1, we're going to square both sides of the equation. And then step 2, we're going to disjoin the fraction by multiplying both sides by q squared. All right, so here we have the squaring of the left and right side of the equation, which we can simplify on the left side to the value 2, and on the right side to this fraction, both basically the exponent gets distributed to the numerator and the denominator as per the rules of arithmetic. And then we end up with this equation here, which gives us a bit more insight into the complexity of root 2. So this proof is a little bit involved in terms of algebraic manipulation, which is great. So the premise p squared equals 2q squared implies that p is even. And what we're taking for granted here is the fact that and this notation that I'm using here, this is kind of an intuitive way of thinking about even and odd numbers and their squares for me. So this is kind of how I am expressing this. Many ways to express this idea. So a number x is divisible by 2, right? And this is just a symbol for true, tautology, right? Valid. And then, here's obviously the symbol for false and valid, all right? So a number x is divisible by 2 if and only if its square is also divisible by 2. So this notion is true if and only if this notion is true. And a number is not divisible by 2 if and only if its square is not divisible by 2. All right, and I don't actually bother with proving this claim or this pair of claims, but if you go online, you can very easily find, and if in a number of textbooks, you can very easily find proofs for these cases. So we show that if x is even, then x squared is even using direct proof. The only if part, or so if x is even, then x equals 2k for some integer k, which again we saw this earlier in our we see this earlier in the College of Redwood's textbook. Hence, x squared is equal to 4k squared, which is another way of writing 2 times quantity 2k squared, which is even, since it is an integer divisible by 2. All right, boom. This completes the proof of case 1. So, so now we see that if x is even, x squared is even. And then this is sort of the reverse case. We showed that if x squared is even, then x squared must be even. Excuse me, if x squared is even, then x must be even. And here we're using the if part of the sufficiency. This is the, all right, so using the if part or sufficiency. And I like this. I like these. I like this note. I like this this use of terminology. So we use a proof by contraposition. Assume x is not even, and then show that x squared is not even. If x is not even, then it must be odd. So x equals 2k plus 1 for some k. And of course, k being an integer. Then x squared is equal to 2k quantity 2k plus 1 squared, which equals 4k squared plus 4k plus 1, which equals 2 times quantity 2k squared plus 2k plus 1, which is odd and hence not even. This completes the proof of case 2. So therefore, we have shown that x is even if and only if x squared is even. All right, so this is sufficient enough, right? These two ideas here to continue working with this notion here. So we should also note for context that an integer squared is an integer. And the reason I point that out is because we can do this mapping, right? This helps with thinking about the proof down the line and arithmetically thinking about other versions of the proof. So I just kind of put it in there. In the particular case, when P and Q are mutually prime, Q is necessarily odd, right? Because if P and Q are mutually prime, we already know that P is even because its square is even, right? And we've just shown that the square of a number is even if and only if the given number is even. All right, so 2 must be, so if 2 is prime, assuming 2 is prime, 3 must be an odd prime number because 2 is the only even prime number that we are aware of. And you know, we're going to look at what kind of proofs there might exist for that notion, or if we just take it as an axiom, which is just as well at this level. So moreover, the square of an even number is divisible by 4. We just saw that. The square of an even number is divisible by 4. Right? We show that if x is even, then x squared is also even. Right? X is even, divisible by 2. X squared is also even, and divisible by 4. All right. It follows that this must be the case. Okay, and again, a bit of MathML in here, nothing crazy. So p squared is equal to this expression, which can be reduced to this expression, which can be reduced to this expression. Now, with this final expression right here, we can see that it is in fact not divisible by 4. Okay, because we end up, if we divide, right, per the rules of arithmetic, what we would have to do is divide this by 4, this term, and then divide this term by 4. We divide this term by 4, we end up with is 2 times this quantity, in this parenthesized quantity, and over here we end up with 1/2. So p squared is in fact, if we assume that P and Q are mutually prime, where P is prime, as denoted as implied by this expression here, and a forcing of Q being odd in that case, we see that we have a contradiction that's generated down here, because if P squared is in fact even, its value must be divisible by 4. We proved that up here. However, it isn't, right? We see that it isn't, meaning that division by 4 does not give us an integer or a whole number or natural number. We end up with an integer plus a fraction, which gives us a mixed number, right? Whole number plus a decimal of some sort. And therefore, there must be, leading us to conclude that Q must be even, a contradiction of our initial assumption regarding Q. All right, and that sort of concludes this proof. So as I said, you know, you have it here. You know, the PDFs for these will be uploaded to my GitHub, and so you'll be able to work through it. And all right, so that concludes this proof 1, and then next video we'll go over a simpler proof. Actually, it'll be the one that's given in the text, and I'll link also probably to another version of that same argument that you can find online as well.